Hello everyone, welcome back to my channel. Recently, my friend Yukida Mayaki-san wants to use the TouchBar screen for some DIY projects. He asked me to help reverse engineer and drive the long screen. I couldn't find any information about it online, so I have to do it myself. In the previous video, I've shown several methods on tackling screens without datasheet. In the first video, I measured the size of the chip and counting the number of pixels, trying to find a match. Then I can use the microscope to look at the ITO and FPC traces to get the pinout. The second video is also using a similar method, but for that screen I didn't need to know the exact driver chip model number. So with the help of a same size, same resolution, and same controller screen, I can derive the pinout, then driving that with a universal driver board. However, these methods are not applicable this time. Apple's screen probably has a custom-made controller, means I simply cannot find the datasheet. This time the idea is actually a bit simpler, starting directly from the original MacBook Pro, probing the signals on the MacBook Pro to understand how to control the screen. The first thing is a hardware connection, basically the pinout of the screen. One can basically probe on the board to derive the pinout. There is just not many signals to begin with, or cheat a little bit by just look at the schematics for repairing. I'm not going to show it here, but the result is a design of an breakout board like this. You can see that the pinout of the screen is indeed very simple. Basically, it has a 3.3 volt power supply and 1.8 volt power supply, one unused I2C channel, and a single lane MIPI DSI. There is nothing else. Next is the software driver. Considering that many viewers may not have played with any MIPI DSI screens before, here is a brief introduction. The MIPI DSI is a screen interface protocol commonly used in cell phones and tablet PCs. The data rate depends on the version is up to 1 gigabit to 4.5 gigabit per second. Similar to the PCIe, it can run multiple lanes in parallel for higher bandwidth. It should be noted that the MIPI DSI is a screen interface, not a monitor interface. So unlike the EDP, which inherited the DisplayPort's plug-and-play feature, the DSI is in some sense a faster SPI plus RGB or DPI 2-in-1 interface. Plug-and-play is just not quite a thing in the DSI world. The host is required to initialize the screen before using, and the initialization sequence can be different for different screen models. The main task in writing the driver is to know what needs to be sent over during initialization. The answer to that is hidden in this MacBook. I should be able to just use a logic analyzer to grab whatever it sends over and just use it. However, there is a problem here. I do not have any particularly good logic analyzers on hand. The best one I have right now is this digital discovery. Although the 100 meg sample sampling rate is pretty good, it does sound a little bit slow compared to the gigabits rate on the MIPI DSI. But that's not entirely hopeless. The MIPI DSI has two transmission modes, low power mode and the high speed mode. The former speed is anything up to 10 megabit, while the latter speed is 80 meg to gigabits. Generally speaking, the screen initialization will be completed in the low power mode, and then it switched to the high speed mode for sending data. If the initialization of this TouchBar screen is also done in the low power mode, then it should be easy to see the data with a 100 meg sampling rate logic analyzer. However, it should be noted that the low power mode uses 1.2 volt signaling, so the logic analyzer should support adjusting the threshold level. So here I do have some data. It seems quite reasonable. Because the digital discovery software does not support MIPI decoding, I export it to a CSV file, then do the processing later. I've imported the waveform into GDK Wave so we can take a look at what's going on. First of all, there are a lot of big chunks of data here, which is likely transferring the pixels onto the screen. If I measure the interval between these chunks, it's just under 17 milliseconds, which corresponds to a refresh rate of around 60 Hz, as expected. However, if I zoom in, there is nothing there, which is also expected. The voltage is just too low in high-speed mode for the logic analyzer to see anything. Looking at the signals here, looks like some data transmission in low power mode. But what exactly is it transmitting? So it's time to take a look at the MIPI low power mode transmission protocol. There are two data lines, P and N, which forms a differential pair in the high-speed mode. But they are two separate single-ended signal lines in the low power mode. Both lines are high when idle. When starting a new transmission, it first performs this escape mode entry sequence, then starting to send the data bit by bit. There is no clock line. A pause on the P line means bit 1, and a pause on the N line means bit 0. After the transmission is completed, there is a stop sequence where both lines return to a high state. So I wrote a simple script to implement a small state machine to decode the data received. Run it, and here is the received bytes. Do they make any sense? In the low power mode, the first byte sent indicates the mode entered, and there are several possible values. The ones received here are all 0x87, which means that it enters LPDT, low power data transfer mode. That is to say, all of the packets sent later are one or more MIPI packets. MIPI packets can be categorized into short packets and long packets. Short packets only have 4 bytes of header, while long packets have 4 bytes of header plus data payload plus 2 bytes of checksum. The first byte of each packet indicates the packet type, such as whether it's a command or a pixel, a long packet or a short packet. For short commands, the command is the 2 byte in the middle of the packet header. For long commands, these 2 bytes indicate the length, and the data after the header is the command content. Inside this boot sequence, the Mac is sending quite a few commands, some of which are non-standard, while others are more straightforward, basically setting the resolution range and then turning on the screen. The initialization sequence is fairly short. In fact, the TouchBar screen has a dedicated SPI flash directly connected to the screen controller, so it's pulling most of the configurations there instead of relying on the host to write them during boot. In terms of implementation, I can use some hardware MIPI controller, or I can just do GPIO bit banging. I'm using this NXP MXRT1176 microcontroller evaluation board here. The microcontroller has an integrated MIPI DSI controller. Sounds like a good fit. If I just try copying and pasting the sequence directly and then run the code, the screen doesn't seem to be impressed. That's strange. What went wrong? So I tried GPIO bit banging, still nothing. At this time, I realized that after switching to the GPIO bit banging, I'm now only driving the data lines, not the clock lines. They are floating, which is not good. I then added 2 resistors to pull these lines high. Turned out it now works. I tried more stuff and finally narrowed down the cause. The screen requires the clock lane to stay high or basically inactive during initialization. NXP's example code enables a high-speed clock as soon as the screen is out of reset. Generally, this is okay, but this screen in particular just doesn't like it. Okay, now the screen is initialized. The next step is to get it to display some image. This brings us to the 2 modes of operations of the MIPI screen, command mode and video mode. Command mode is like a common SPI or 8-bit parallel screen where you send commands to control the screen or write pixels. The video mode is similar to the controllerless screens that require sending video data and HV synchronization signals continuously. Both are done by sending MIPI packets, but the type of packet sent is different. For example, in the table of packet types, there are synchronization packets as well as pixel packets of different formats. These are used in video mode. Note the difference between low power mode and high speed mode as mentioned before. MIPI commands can be sent in both low power and high speed modes. Video should only be sent in high speed mode according to the specification. Back to the driver code. To use the video mode, that's basically enabling the hardware LCD controller and the DMA, connecting the LCD controller output to the DSI controller, and run the code, it doesn't work. This is not exactly unexpected. The DSI screen video mode also has several different options, such as the clock can be always running, or it can also be gated during idle. During the blanking period, the controller may send blanking packets or no packets, or exit the high-speed mode and return to the low-power mode. For the synchronization, it may only send the synchronization start packets, but not the end packets. It could also send both. Generally speaking, based on my past experience, the screen does not support all these combinations. There might be only one or a few that works. Also, blanking length and the synchronization precision are also a bit tricky, but generally getting these wrong resulting in an image being in the wrong location or just a black screen, not like this, which is completely unresponsive. However, after trying all combinations, it just doesn't do anything. One possible guess is this screen doesn't support video mode at all. It's a pure command mode screen. I tried writing pixels with the typical 2C and 3C pixel write command. Yes, they do work, but I just want a confirmation that this is indeed the case. Turning back to this MacBook Pro, As mentioned earlier, I cannot see the signals in high-speed mode with a 100 meg sample logic analyzer, so I will take a look with this 2 gig sample oscilloscope. However, due to the lack of better differential probes, combined with the totally not impedance-matched Bosch wires, the results aren't the best. I can only say that I hope that this relatively bad signal can still tell me which command was sent. Similarly, I exported the waveform to a CSV file, then wrote a script to decode the data. MIPI in high-speed mode first has a synchronization sequence, after which is the transmitted data. The definition of the packet is exactly the same as in the low-power mode. This synchronization sequence is evident from the waveform here. It's true that the error rate is quite high here, so the results aren't reliable. Here, it seems like if these packets' headers are to be believed, what is being sent in high-speed mode is not a video mode packet, but still commands. The command is exactly 0x3c, which is continuous pixel write. This basically confirms my previous guess that this is a pure command mode screen, and in high-speed mode, it's just sending more commands faster. So I modified the code to let it send 3C in high-speed mode, and it's done. However, a small issue is that the MXRT's LCD controller does not natively support pure command mode DSI screen. The integrated video DMA in this case is kind of useless. But of course, I can still use general purpose DMA with some glue code. This issue may also prevent this screen to be used with other chips with MIPI interfaces that only support video mode screens. So that's it for this video, and see you next time.